Hey, it's me again, and today we're going to be looking and studying the solubility product. So, the solubility product is very similar to KEQ, or the equilibrium constant. So, saturated solutions form an equilibrium. So if we have a saturated solution right here, let's take a look at maybe another beaker. Okay, and in this aqueous solution, we have, let's take a look at barium sulfate. So we have some solid barium sulfate here that is sitting on the bottom, and what is happening is this has formed a saturated solution. So the solution is completely full of barium ions and sulfate ions. Now, these barium ions and sulfide ions are constantly crystallizing and becoming a solid. Okay, we learned this in a previous lesson. And these solid barium sulfate ionic solid compound here is dissolving and is becoming ions. So the solution, the concentration of Ba2 plus and SO4 2 remains constant. But constantly everything is, there's a forward reaction that is constantly happening that is dissolving, and there's a constant reverse reaction that is constantly happening of crystallization. And this stays at equilibrium. Now, so what we can say is a constant can be obtained as long as the temperature is constant. As long as all the conditions are constant, then we can get a constant number out of it. So let's take a look at this equation right here. So again, we have BaSO4 solid, and that is dissolving and becoming, just like the picture above, barium ions and sulfate ions. Aqueous and aqueous. Now, so BaSO4 is dissolving and becoming Ba2 plus and SO4 2 minus, and Ba2 plus and SO4 2 minus is crystallizing and going backwards and becoming a solid. So it's an equilibrium reaction, and we show the double arrows again. So since it's an equilibrium reaction, we can come up with an equilibrium equation. So instead of calling it KEQ, since it's a solubility question, we call it, instead of KEQ, we call it KSP for a constant for the solubility product. And this is going to equal, just like our KEQ questions, it's going to equal the concentration of Ba ions multiplied with sulfate ions. Okay, and that's going to be our KSP expression for BaSO4. Now, same thing for this one. Let's just draw a little bit of a divider right here. Okay, so we have same thing. We have magnesium fluoride. So let's write magnesium fluoride. Again, there's a dissolving reaction that happens that forms Mg2 plus and F minus. Now we have to balance this. Sorry, this is aqueous again, and aqueous. Now we have to balance this. There's two fluorines here, and there's only one here, so we need to put a 2 right there. Now we can come up with our KSP expression. Okay, and just like KEQ, we have to use the same rules for making a KEQ expression as we do for a KSP expression. So again, KSP is going to equal the concentration of magnesium ion multiplied against the concentration of fluorine or fluoride ions But since there's a 2 right here, we square it. Okay, and this is our KSP expression. Okay. Now, you'll be given this chart right here, and this chart has a whole bunch of different KSP values, or another solubility product constants at 25 degrees. Remember, just like KEQ, the only thing that is going to be changing this constant is temperature. So all of these are set at 25 degrees. Now we're given a whole bunch of these right here, and well, we can even look up the one that we just studied, barium sulfate. So a barium sulfate right here, BaSO4, has a KSP value that is 1.1 times 10 to the minus 10. Okay, and therefore, if I had this number and I know the concentration of barium in a solution, I can find out the concentration of sulfate by using this number. Now, let's do a couple questions where we have to use this table. So the questions that we're going to do are going to involve these two values right here. So we're going to deal with lead 2 chloride. We'll deal with that one. We'll have 2 problems coming up on the next slide. And the first problem is going to be about lead 2 chloride, and the second problem is going to be about lead 2 sulfate. Okay, so PbCl2 and PbSO4. So we're going to have to kind of memorize these numbers. So the first one we're going to deal with is 1.2 times 10 to the minus 5, and the next one is 1.8 times 10 to the minus 8. Okay, so we're going to do 2 problems involving these solubility product constants. So here's the first one. Just like I said, lead 2 chloride, and it says, what is the concentration in lead 2 chloride saturated solution? So imagine we have some lead 2 chloride. So we have some PbCl2, and this is going to dissolve and crystallize and make and 2 chloride ions. Okay, so here's the equation that we're going to be dealing with, and if we were to come up with our KSP expression would look something like this. Okay, and we know that from looking on our chart from before, we know that the solubility product constant for lead 2 chloride is 1.2 times 10 to the minus 5 is what the KSP value is. Okay, and for this right here, this is going to be a 1 to 1 to 2 ratio. So just to give myself a little bit more room, I'm going to rewrite this formula here. And so again, it's a 1 to 1 to 2 ratio, or in other words, a x to x to 2x. Okay, and so what we can say is when this dissolves into Pb plus 2 and Cl minus, what it's going to be, we're going to replace these values right here with these values over here. So this is going to be x times, now the concentration of chlorine right here is going to be twice that of the concentration of lead, so it's going to be 2x, and that is squared. Okay? So, or in other words, it's going to be 1.2 times 10 to the minus 5 equals, now this is going to be x. Now 2x times another 2x is going to be 4x squared. 4x squared times x, well, I'm just going to kind of move this formula right up here so you can see it. So again, it's going to be 1.2 times 10 to the minus 5 equals, again, x times 4x squared is going to be 4x cubed. Okay? Or what we can do is we can go like this, and then we can solve for x, and we see that it would be 1.2 times 10 to the minus 5 divided by 4. Now we need to get rid of this side, and so we're going to times this by, or put it to the power of 1 over 3. And that's going to equal x. And I've already done this calculation, and x equals 0.014. See, 2 sig figs right here, and so 2 sig figs right here. And x right here again is here, and so this is the concentration of lead. Okay, or in other words, okay, and that's our answer right here. Okay, so we did pretty much the exact same kind of thing as KEQ. This time though, KSP is given to us, and we just have to look it up on our table. So the other one we talked about was lead 2 sulfate, and we looked that one up on our table, and we remember, if you remember it, it's 1.8 times 10 to the minus 8 is the KSP for that. So this one says, what mass of lead 2 sulfate will dissolve in 500 milliliters of water? So always start off with a formula, so I'm going to do that. I'm going to write down Pb SO4, and that makes lead ion and sulfate ion. Okay, so, or in other words, this is a 1 to 1 to 1 ratio. So what we want to find out is the concentration of lead 2 sulfate. Okay, and then with that we can figure out the mass of lead 2 sulfate. So again, our KSP formula, our KSP is going to equal the concentration of lead times the concentration of sulfate and we're going to replace this with a few values. So again, the KSP according to our table is 1.8 times 10 to the minus 8 is the KSP for this. And this is x, and x, or in other words, x times x is x squared. And if we solve for x right here, we can find the concentration of PbSO4, and x equals 1.34 times 10 to the minus 4. Okay, now this isn't our final answer yet. This is just an important step though. So again, this is not our final answer, just an important an important number, so I'm just going to circle it right here. So this is the concentration of PbSO4. It also happens to be the concentration of lead in solution and SO4 2- in solution. Anyways, we're going to use this number right here to calculate the mass of this. So again, we're going to use 1.34 times 10 to the minus 4 concentration, because this is a concentration, and we're going to multiply it by our volume, because if you remember, concentration is moles per liter. So if I multiply by our volume, then this will be the amount of moles of lead 2 sulfate. So we're going to multiply this by, since this is moles per liter, I'm going to multiply this by liters, which happens to be 0.5 liters. This is a half a liter. Okay, and then I'm going to multiply by the, so now after I do this calculation, just this times this, is moles of lead 2 sulfate. And what I'm going to do now, I'm going to multiply by the molar mass in order to get the amount of grams of lead 2 sulfate. So the molar mass of lead 2 sulfate is 303.3 grams per mole. Okay, and if we do that calculation, we find that we get an answer of 0.020 grams. Okay, and this is our answer. Now, our final answer here is 2 sig figs, and the reason being is because KSP does have sig figs, so that table does have sig figs, and this happens to be 1.8 times 10 to the minus 8, so this is 1.8, this is 2 sig figs here, and I should have left this as 2 sig figs as well. So this number should be a 2 significant figure number. And so that is the smallest amount of sig figs in our question. And so our final answer is also a 2 sig fig answer, okay, which is 0.020 grams of lead sulfate.